Hi everyone. Today we have a faulty power supply and I'm going to show you how to fix it. I acquired this one from my workplace, which is withdrawn from the service. It doesn't gives the right voltage and it gradually decreases the voltage. So today I'm going to show you how to fix it with slight reverse engineering and using one of my thermal imaging Cat 5, Cat S60 camera. So let's get started. Okay, here we have DC power supply, model 3010D, and I guess this is 30 stands for 0 to 30 volts, 10 which is 10 amps. Let's power this one up and let's see what's happening. Okay, let's set the voltmeter to DC and it's powered up. Okay, we have 30 volts. Uh, 33, and you can see it, the voltage is gradually decreasing. But you can also see from the multimeter. So obviously there's a problem inside, so we don't want to turn on this one for so long. Otherwise, if there's some components inside that's overheating, that will damage it further. So you can see that it's overloading the current. Okay, we'll switch this one off now. Okay, let's power it up again and let's short the output and decrease the voltage. This is to see if there's enough current drawn. So it gives us 10 amps, which is true. So it's on the model number. But the problem here, the problem here is the voltage is dropping. 9.7, 9.6. So there's a problem. So now we are going to have a look inside what's wrong. We're using our thermal imaging. We'll see if we can see some overheating component. Okay, let's open it. So with regards to electronics, I have almost 30 years experience with electronics as well. So I fix most of the electronic stuff at work, and also I build some project or test equipment for testing as well. So here we go. So as you can see, not much of the switching power supply. There's not much inductor, so it's very linear power supply. It has four transistors at the back. Okay, now what we're going to do is to see if we can see any overheating component. So it's a pretty good, as you can see. So you can see in the desk, you can see my hand. If I place my hand on my desk and remove my hand, you can still see the print, which is it leaves the heat on the surface of the desk. It's pretty interesting. So we use this one for finding overheating component. So okay, let's get started with this one. Let's power it up. So now we have 9.3. Okay, we have a look what's happening. Let's see if we have some obvious let's bring this one a little bit closer with the light. Oh, you can see that there is heating, but it's strange that the power transistors at the back is only it's only 17 degrees centigrade, so it's not really operating. So let's see if on the circuit board there is one part there which is really, it's getting really hot. So there is one part there which is, it's 126 degrees centigrade. It's increasing. It's 100 and it says at 126 degrees, which is really hot for that particular component. And some of the parts here, which is the mains, it's only 19 degrees. Transformer is pretty cold. Not quite. Yeah, it's cold. It's only 19 degrees. But this part here, the top is 121 degrees, 121.8 degrees. So it's obviously something is loading, and the voltage now it's gradually, it's dropping 6.5, 6.2. So yeah, this is a really good instrument to find a faulty component. So you can either touch with your hand, but obviously that really hurts. It's really hot. Imagine it's 130 degrees. You can't touch it. It's like touching a tip of the soldering iron. Soldering iron is normally at 270 to 320 degrees, a normal operating condition. So okay, let's find it out. What is this component? We have to take this mains power off. Just make sure that we don't get shocked. So we know that the problem is this one here. It's obviously that it's heating up, but we can't tell that this is faulty because it's heating up. That means it's drawing too much current, and that means it's operating. It's overheat, but problem is it's overheating. So there is other component, or there are other components around this area that's causing this chip to overheat, and we'll have a look what is chip number L7812CV. So obviously it's a 12 volts regulator. So for the 12 volts regulator, this okay, like that. So this is 7812CV, a 12 volts regulator. So this one here, this pin 1, 2, 3. So this one here is the input. This middle is the ground, and the other one on the right hand side is the output. So the voltage regulator, 12 volts regulator, is the ground is not always the ground. Sometimes it's a floating ground or offset ground. So with respect to the input. So the output with respect to the ground, I mean pin 2, it's always should be 12 volts. This one here can go from has to be above 12 volts, 13 to 30 volts, and it regulates down to 12 volts. So we'll have a look. We'll have to trace where this 12 volts going. Okay, what we have here now, that's 48. That's the input supply, and with respect to the ground here on the input supply, we'll test the input of the voltage regulator. We have 33.2 volts and output is 11.551. It's dropping. So when you test between output and the ground, we should have 12 volts regulated, but at the moment we only have 2.96 volts. So obviously this one is loading. Something's loading on the output. So we'll switch this on off. Okay, now we have to do a resistance check. So we're just trying to follow the output of that regulator. It goes to a capacitor, which is and we'll check with the resistance on the capacitor, but that's in ohms. Make sure that we unplug that one. It's 0.8.7, 9.8k. So it doesn't, seems like the ground and output is shorted. So the question is why it's loading, why it's loading the output. I don't believe that the regulator is faulty, but we need to try to find it out. So one thing is checking between ground and output for resistance check if it is low resistance. So looking on the multimeter, it's not. So that means that the output is somehow biased with negative voltage somewhere. So that's the other way of loading the output when the resistance is high, when the resistance is not low. That means it's not due to the low resistance between output and ground or middle of center pin. So this is something due to a negative voltage which is biased into the output voltage. So the only possibility for this case is if you have op amp. If the regulator is supplied into an op amp, which is the op amp is powered split supply. It's not a single supply. I mean, split supply is you have positive voltage on, let's say, for dual op amps, normal pin configuration is pin 8 is the, am I right? Pin 8 is the supply voltage, which is a positive, and pin 4 is the negative voltage for split supply. So we'll see if there's op amp connected to this voltage regulator. Take this board out and have a look at from underneath if there's op amp. If not op amp, some are transistor in push pull configurations. Okay. Okay. There is a, you can see there's a 8-pin chip. So okay, we'll see if this one is connected to that. If pin 8 is connected to the output pin. So we'll connect this on pin 8 here, and this one on the output pin. Oh, so that's connected there. So definitely this is a candidate for a possible fault. Now The only possibility of this one, as what I said before, is when the output voltage is biased with negative voltage. So having this chip here, I believe this is a op-amp, because normally with linear power supply, usually op-amp is very common. Okay, we'll have a look what's the number of this. It's an LM2904P. Okay, so it's an LM2904P. So we'll Google this one. Okay, so the LM2904P is similar to LM358, which is a very common op amp. So pin 8, 1, 2, 3, 4, 5, 6, 7, and 8. So pin 8 VCC, that we confirmed that the VCC is connected to output pin of the 12 volts regulator, and so the ground is this is definitely what we suspect. This is biased with negative voltage or a negative VCC. We have to connect this one again, and now we will see if we can what's the voltage, measured voltage on pin 4 of this chip. Okay. Just wanna screw this one back. It's to secure the board while probing the pins. Okay, let's power it up. Let's power it up just again. We'll set the voltage to DC voltage. Switch it on. Now, with respect to, we have to make sure that pin 4 with respect to the ground, or pin 1, the ground of the voltage regulator. Okay, this one here, then, and pin 8. Okay, this is pin 8, which is 4.6 volts, and pin 4 is on the other side, which is 0.9. Sorry, yeah, 1, 2, 3, 4, 5, 6, 7, 8 there. So that's pin 4 here, 0.9. Okay, let's just turn this one off, and we will measure the resistance between pin 8 and pin 4. Okay. So resistance check between pin 8 and pin 4. 11.9 ohms, which is pretty low. Must be faulty. This chip must be faulty then. I have some components here. I'm sure I have a LM358, and we'll check the LM358 chip between pin 8 and pin 4, and what's the resistance check. Okay, here we have LM358 chip. Made by Texas Instruments. Okay, let's try with pin 4 and pin 8. Oh, that's 6 meg. What about this one? 4 meg, 4.3 meg. Oh, so okay, so I think we found the problem. So we'll take this, we'll unsolder, we'll take this chip out, and we'll see how it goes. Okay, we'll solder this chip, and we'll see how it goes. I have some solder braid. Temperature of the soldering iron is too low. I need to set it to 300 degrees. It's easy to desolder the chip if you put a little bit of solder. So when you put this solder wick, it's easy to flow the solder and to remove. So we'll put a little bit of solder on the chip, on the pins. Okay. Maybe most of you are thinking why I'm using a solder wick. Where solder wick is not cheap. The reason for that is don't have the soldering sucker. So I don't have any problem in using a solder wick. So I'll do this one. Somehow the solder wick doesn't work that good. So what we can do is we'll take this one out. So we place a tweezer underneath the chip and we pull it out. So we put more solder. I mean, solder the whole. Put more lead on all the pins. Okay, here we go. We're able to remove the chip. So now we have to clean this one a little bit. We have the solder blob here. Just take it out. Make sure it won't short circuit on other components. Now we can use the solder wick to clean the pads. maybe you have better idea or better ways to desolder this component, I'm sure, and it's up to you how you do it, as long as you take the parts out and make sure that you don't damage the pad. So there's one which is not it's not clearing the solder. One of the reasons this one is the heat is not, I mean, hot. It's not hot enough, so we have to increase the heat so it will melt the solder quickly. Try it again. It's only pin 3 of the chip. Okay, great. It's all clear. Okay, now I put this one aside, and what we're going to do is to check this one if it's shorted. Okay. Check for resistance check. So we need to check between pin 8 and pin 4. Okay, so it's not shorted. So there's the problem is somewhere else. So it seems like this op-amp still good. We have a 5.76 meg reading. So now we have to check this pin here, pin 8 and pin 4. We still have the 11.4 ohms. So now now we have to find where and why this output of pin 8 and pin 4 has a very low resistance of 11.5 ohms. Let's find it out. Okay, before we find the short or low resistance circuit or about, we'll check if we get the output voltage of this this regulator to 12 volts while the chip was removed. So let's power it up and we'll have a look. Hopefully this won't affect the regulation of the voltage or damage any other component while the chip is removed. Okay, let's see. Place this one here. So I'll check for the output. We have 5.5. Which is still low. So we check from our thermal camera if it's still overheating. Okay, let's power and switch this on off first because we're not ready yet. Okay. Okay. Okay, that regulator is still, the 12 volts regulator is still overheating. Still going out to 111 degrees, 112, 113, 114. So we'll keep checking and find what's the problem. Okay, we'll keep checking. So we'll say, we'll find where it is output of the voltage regulator is going. So we have to trace where it is going. It's going this way, and here. So it seems like there's still another 8-pin chip which is connected to the output of the regulator. So we'll have a look at what's this chip. Okay. We still have another IC here, with another 8 pins, which is LM2904P, which is the same chip, or the same as LM358. So maybe this is the problem. So I'll take this one out. Okay, we'll desolder this chip. We'll try with maybe, because before we didn't able to desolder the chip because of the temperature of the soldering iron. So we'll see if we can get this one out with solder wick. It seems like it's working. Seems like they're able to desolder with solder wick. So that comes loose now. Here. Okay. Okay. Get this twist underneath the chip. Okay, here we go. Okay. managed to get this chip out. Now we'll see if the resistance increase between pin 8 and pin 4. Okay, that resistance gone to 0.3 meg. Wow, I think we found a problem. So that's really good, really good. Okay, so we can quickly check the voltage of the regulator, the output voltage of the regulator, if we get the 12 volts output, but we can't keep it for so long, hoping that it won't damage anything, because normally without the proper op amps regulation, it can cause overdrive to the transistor. It could damage the transistors, and because we really don't know the overall circuit of this power supply. So, and also we don't really need to understand the overall circuit. So just only focus on what problem that you found and how you solve the problem. Let's say for this one, we found that the regulator, voltage regulator, or this one chip is overheating. So we found out that the voltage output is not regulating. We don't get 12 volts output. So that's why we have to focus on that part only, and we don't need to understand the overall circuit or construction of the power supply. But we knew that some basic circuitry, like the bridge rectifier and filter, and some of the transistor biasing between base emitter, which is has to be 0.7 volts for silicon junction. So yeah, so we really don't need to understand the overall circuitry, especially with this front panel, on how this front panel works. Especially we don't have the diagram. So now we check for that for this regulator, output of the regulator, but we have to quickly do this one, and I don't want to turn this one for so long, because I'm afraid that it may damage some other component, because we don't have the op-amp regulation properly regulating the voltage. So we'll check this one. So the output, we have 12 volts. Oh, beauty. So it's now we get 12 volts output now. So we don't have to power it up for so long. So now we have to check this this chip. Okay, we'll check the, sorry guys, was running out of battery, so here we go, we're back. So now we check for resistance check between pin 8 and pin 4 of the chip. Here we go, it's 11.4 ohms, so that's definitely faulty. Okay, I think we found the problem. So now we have to replace this chip, but I really would like to replace both with the same type, LM358. So we'll do that. Okay, so we'll replace the chip. Make sure that we unplug this main supply before doing that. Always keep in mind. Okay. So first one is we have this LM358 chip. I see. Okay. So that's this one is pin 8. So we need to position underneath. Pin 8 is this. Okay. Well, anyway, there's also a marking. Okay, it doesn't go straight, so we have to bend this pin. Also the other one, you can use it with. Well, with this one you can, there's no problem on touching the pins. Wait, I dropped it. There's no problem on touching the pin because this is not really a sensitive, easily sensitive device, unlike when we are working with CMOS. So there's no drama. Okay. So that's in. So we have to hold from underneath while soldering. I have to solder one pin just to hold the chip. Okay, that's good. Okay, now we have to solder the rest of the pins. Okay, that's pretty good. Okay, next one. Okay, I'll check with the magnifier. So the LM358 is this one, the other one. Okay, we'll bend, we'll straighten the pins so it's easy to insert. Okay, I think that's all good. And now let's figure this one out first. Which one is pin? Okay, that's easy. Okay. It's not going in, so okay, it's going in. Okay, maybe some of you you find it easy to hold the lead while also soldering, but I have my other hand underneath, so I only have two hands, so I have to do this. Okay, all good. Now solder the rest of the pins. Okay, now we have to test for resistance check. If there's no short, we check between pin 8 and pin 4. So we have 2.18 meg, which is pretty good. Now we have to put this one back. In my future YouTube video, I really would like to show you how to fix VCR or DVD. Sorry, not DVD. VHS player, which is a very old unit. Maybe some of you haven't encountered this old VHS player, but it's a good thing to know. Okay, now it's the verdict. We'll see how it goes. Check for the DC. Okay, now check for DC, apply the voltage, and finger cross. Okay. Oh, 45. Is it 45? That's I think they still have a problem, but we'll see. So we check the voltage first, the voltage of the regulator on the output. That's 12 volts. This is pretty good. And check for the pin 4 of the chip, 8.98 and 12. With respect to the ground of the 12 volts, but with respect to the ground on here, it's not 12 volts. So the output here is 33, and sorry, the pin 8 is 33 and pin 4 is 12 volts. So it seems like they still have problem with the negative voltage, because the voltage here as CV is on, and it goes 45, 46, so which is it's likely to damage the circuit again, again. So what I found here is the op-amp pin 4 voltage supply is 8.98. So normally when you have 12 volts on pin 8, you should have a negative 12 volts on pin 4, but we only have negative 9 volts, so still not operating properly. So we still have a problem. But now the CC has gone, but we have the problem in the voltage output. So we'll check what's the with our thermal imaging camera if there's anything overheating. Okay, so we'll check if something's overheating. Check with our thermal imaging camera. Okay, this is it on. Check for that regulator there. It's only 19-20 degrees, so it's not overheating anymore. So most of the circuit board circuitry is at is 21 degrees centigrade. Let's check for the front panel. We have to turn this soldering iron because it's interfering with that. 27.8 degrees, 28 degrees. Transformer is 20 degrees. The bridge rectifier is roughly at 20 degrees, and transistor at the back. Okay, let's have it. Transistor at the back, it's 19-20 degrees, so it's normal operating condition. So there's one here which looks like very hot. Somehow we don't know what it is, but it's heating up. 27 degrees. It's about 25 degrees. So that's the first 358. There's another one here which is it's 27 degrees. So I'm not sure what's underneath, what's heating up. It seems like a resistor inside. There's one transistor which 44 degrees. That resistor there is really heating up. So now it's 45 degrees. It's a resistor, it's a power resistor underneath. Okay, we'll have a look. What is this resistor? We'll measure the voltage across that resistor. Okay. It's about 21.6 volts, which is a lot. Between resistor voltage drop of 21.6 volts is a lot. Okay, let's turn this one off and check for the resistance again of the resistor. Reading is not stable at the moment. Let's wait. Maybe this capacitor charge. So check for the DC voltage on across the capacitor. So we still have 17.5 volts across the capacitor. So we'll wait until it discharges, because I don't have a bleeder resistor here, so the only thing we can do is wait. Okay. 12 volts is dropping. So we're almost there. We almost find the problem. At least we find one, which is the chip, but we still have another problem. So especially the pin 4, which is the negative bias, negative volt supply of the op amps, which is only 8.9 volts, minus 8.9 volts, which is supposed to be equal to roughly close to minus 12 volts. Okay, now our focus is to find out why the pin 4 is only minus 8.9 volts, which is supposed to be minus 12 volts. So either way, there should be negative 12 volts regulator, but it seems like I can't find any negative 12 volts regulator. So we have to figure out and find where this negative 12 volts coming from. With the resistor that's heating up at 45 degrees, I think it's normal. We measure the resistance, which is it's a 1K resistor. So 1K resistor, and it seems like it's 2 watts. So for 1K, we have 21. The voltage is 21 volts across the resistor squared 441 divided by 1000, which is 1K, gives us 0.44 watt. So the dissipation, the 21 volts across the resistor dissipates only 0.4 watts, 0.44 watts, and resistor is the size of the resistor is roughly 2 watts, so that's fine. So that's not a problem. Now the problem is the supply on the pin for the 2 op amps, where we have to focus with looking for where it's coming from. So maybe we can use the beeper to trace where this going. So we'll say this is pin 4, so it's not going here, so it only goes there and to the other chip, to the other LM2904P IC. So definitely not, it's not coming from that side, because there's no other connection towards that chip. So we have to go on the other direction. So with this one, and then we'll check what are these components is connected between along the trace. So these components here underneath, we have a look. There's a diode. So next to the diode is it's a resistor. So it's a quite big resistor. So it's not that. Well, it's a capacitor. So we have to keep looking. So that point on here, so there's another terminal here along the strip, along the track. So it's a capacitor, so it's not that one, definitely, which is across between the pin 4 track and the ground of the center pin of the voltage regulator, the 12 voltage regulator. As I believe that would be the reference, the zero what do you call this, floating ground, or the reference ground. So we keep looking, it goes here. So there's 2 terminal there. Have a look, that's capacitor. It's a capacitor, so that's a capacitor between the trace and the reference ground. So another terminal here, which is a jumper. No, it's not a jumper. What's this? Oh, it's a resistor. It's called R91, but it's burnt. It's burnt. Okay, so yeah. So that's obvious that the supply is coming from here, because it's very tiny, only 0.4, 1/4 watt resistor, and it's badly burned. I can't really see the color. It's badly burned. So this resistor is coming from this guy, what's this, and this one across the resistor, across the badly burned resistor, is a capacitor. It's 220 microfarad 35 volts capacitor, and that's definitely not that one. So what we suspect here is not a capacitor, it's supply voltage from negative supply. So keep looking. So that is a diode. So here is connected to diode. So we set this one to diode. Okay. So 0.5. That's a forward voltage. That's a reverse. So this one is a negative voltage coming from here to that point, and I believe that this must be coming from one of the output tap of the transformer. So there's two diodes here. So if this is the negative side of the diode, which rectifies the, I believe this is this two terminal here after the two diode is okay, it's coming from this line, which is it's a blue wire, blue and the black wires coming from, let's try this one. Okay, it's coming from the transformer. So that's supply to the negative voltage of the op amp. It's coming from the transformer through the diode. We'll check the diode if the diode is good. So to make this negative voltage to this line here, this must be forward voltage. Yeah, which is true. And this is reverse. And this one should also be forward voltage, which is true. And this is reverse. Okay, now the problem here now, we found that the problem is that resistor, burnt resistor. And to know the value, we don't know. We'll figure it out. That's easy. There's no we have to put this one back. There's no really critical value to put that one in. As important is you get the bias voltage. So we have to, the only way to find it out is to calculate the resistance and expect what is the current supply to the op amps. And the resistor is just current limiting, or could be acts as a voltage drop. But if the supply voltage from the rectified signal is close to -12, then that resistor is close to 10 ohms roughly. Okay, we'll power this one up and we will measure the voltage. And our reference ground is the center pin of the voltage regulator. So okay, we'll set the multimeter to DC voltage. We power this one up and we measure what is the voltage across the diode. So this one here, this guy here, that is -24. So yes, definitely you cannot and you can't short the one or connect the one directly to the op amp. That is way too high, -25. So we need to drop that one through the resistor. But the problem is we don't know what's the value of the resistor. So to find it out is we need to assume, or we need to find out what's the current dissipation or consumption of the op amps. So from the data sheets, the maximum, we just assume the maximum I'll come back to you shortly. Okay, I'm back. So looking on the data sheets, the output current, so the supply current at 15 volts is roughly 750 milliamps. So now we have 25 volt supply. Let's say we have negative 25 volts across a resistor into minus 12 volts, and we have to find out what's the voltage drop across this resistor here. So to find out the voltage drop is the VR, which is equal to the current times the resistance. So but we don't know what's the resistance, so we have to transpose this. So R is equal to V over I, which is equal to voltage drop across this is 25 minus 12 divided by 750 milliamps. So 25 minus 12 divided by 0.75 is 17.3 ohms. Okay, so to give a little bit of margin, we need to increase that resistance. So we have to choose R is equal to roughly 20 ohms. Unfortunately today I don't have that resistor at the moment. I'm lucky if I have one, and we have to check what is the dissipation of these resistors. Why they choose 1/4 watt, 20 ohms at 750 milliamps. So the voltage drop across this is 13 volts. So the power dissipation of this one is equal to E squared over R, or equal to I squared R. Either way, which one you want to use. So if you want to use a voltage or the current, then I squared R is equal to 0.75 squared times 20 ohms. So what's that? 0.75 squared times 20. So 0.75 squared times 20. It's not true. We get 11.225 watts. So that's definitely wrong. So for the E squared over R, which is 13 squared, maybe wrong. I squared over R. Sorry about my formula. E squared divided by 20, 8.45, which is still not right. Okay, we'll come back to you shortly. Okay, the formula is correct, and it seems like using 20 ohms, 13 volts, we have to dissipate roughly 8 watts, which is not right. So we have to find the resistance based on the original wattage of the resistor, which is 1/4 watt. So 1/4 watt, so we have 0.25 is equal to E squared over R. So R is equal to E squared over 0.025. So I have to find the value of R, which is 13 squared divided by 0.25. So 676 ohms. So having a 676 ohms, there's no value around 676 ohms, so we have to either use 470 ohms, or the next one is 680 ohms. There's a 560, I think. No, it's still 560, 680, or we can use 1K. We'll see how it goes, but having 680 ohms, the current is only 13 volts divided by 680 ohms. Times 1000 in milliamps, so 19.1. So the current is only 19.1 milliamps. Oh, that's strange. Because what I expect is 750 milliamps, but based on the calculation and the rated of the resistor is only 19.1 milliamps. So we'll see how it goes. We'll replace this one with either 680 ohms or 1K. We'll see. We'll find out. Maybe I have some resistor floating around. I'll be back. Oh dear, I have resistor, but I don't know if I have some values here. It's a lot. Okay. Oh. It's a lot of resistors, and we'll see what are the values. This one here, this one in one pack, they're all the same. So it's more than, I think it's more than 1,000 inside one resistance. So 181K. So that's not the value that we're looking for. Okay. This one's still in 2K. This is 220K, I guess. Sorry. Yeah, 226K. This is red, yellow. No, that's not the right one. So this red, 240K. It's not one. Still yellow, the third band, still what we're looking for is red in the third band. So this green on the third band. So that one. Yellow, the third band. This is really challenging. I mean, really difficult to find the resistors on all this all mix up. I don't think so. You can wait for me looking for the right value. I'm just looking for the third band color. This is red. This is 1 point, I think this is 1.8K. Yeah, 1.8K, very close. Let's see what else. Oh dear, too many resistors. This 1.8K. We're looking for brown, black, and red color. This is 815 ohms, so okay. I think this will be what a mess. Okay, this is a good start, we'll see. Let's get this one. Let's try this one. But we'll just place this one on the top so it's easy for us to, but we have to remove the old one. Okay. Okay, see, not sure if you can see this. See, that's badly burned. Okay. Now we just solder this one on the top. Let's get this solder wick. Solder lid. This one solder here. So we just place this on the top. So now we're doing a trial and error. So we'll see how it goes. Finger crossed. Okay, we'll power it up. DC voltage. Let's see. On. Check the negative voltage to pin 4. That's about minus 17 volts. So, but still, okay. It seems working now. So the voltage supply here on pin 8 we have 11.8 volts, On pin 4 we have 18.39. Not quite familiar with CV. I'm not sure if that CV always stays on all the time, but now the voltage is very stable. We set the voltage to 20 volts. It's not dropping anymore. Okay, so we have to set the current to the minimum, and we show this one. We show the output, and we'll see if how much current it draws. Okay, gradually increase the current. We're drawing 1.4. We have to see if this not overheating. 1.2. So we quickly ramp this one to the maximum, and we'll see if we get 10 amps. Okay, that's 10 amps. It's getting hot. Okay, it's 9.6. So it seems like it's working. Okay. So 19.9, and see if this one is not heating up. We'll check what's the voltage drop across this. 6.8. So the voltage across the diode after loading is not 25. Oh, it's still 25. Okay, so now we have to work it out what's the current to the chip. So we have 25 here, or yeah, roughly 24.7, 25, and we have a voltage drop of 8.12. Okay. So we have to change the resistor value. I have to turn this one off. Okay, we have a voltage drop. We have a supply voltage of 25 volts. Voltage drop of sorry, how much is that? I forgot. Okay, 8.3. 8.3 volts. So we have 18 minus 18 volts here. So the current here at the moment is because we have we have 820 ohms resistor. So the current is equal to 8.3 volts divided by 820 ohms. So 8.3 divided by 820 ohms. So times 1000. So it's drawing 10 milliamps, which is very low. So if we have 10 milliamps draw, and if you have again, if you want to drop by minus 12 volts, so we still have 13 volts here at I is equal to 10 milliamps. What's our resistance? Our new resistance value is equal to 13 volts divided by 10 milliamps, which is 13 divided by 0.01, 1.3k. So our resistance value is 1.3k. So I believe that the resistor value is close to 1K, because we have we place 820 ohms, and calculated value, the new calculated value is 1.3K. So the value is likely to be 820, sorry, likely to be 1K. So for now, I don't have a 1K for me. I'll come back and I'll see if I can find one. Okay, we'll have a look at what we have in here. Okay, this one. Okay, we have brown, red. I think this is 1.2K. Yes, it's 1.2K, which is close to 1.3. Our calculation is 1.3. So this will be the final. So we'll see. But we don't want to solder this one at the back, so it's easy to solder from the top. Take this one out. Let's see if we can bend this. That's it. Okay. Solder that. Sorry, didn't see that. I'll place this one on the top. Okay. Okay. Now we have to test it. We'll see. Finger crossed again. Okay. We'll see what the voltage is. Okay, turn it on. We're at 19.4. Very stable. In this position, 20 volts. Okay. We'll check for the voltage drop across this resistor here. This guy. It's 8. It's 9.78. Okay. So now we check the voltage on pin 4 of the op amp. It's 15.5, which is good. That's what we expect. 15 minus 15. And pin 8, 12 volts. So, which is good. And now it's fixed. The voltage is very stable, and with enough current, with the current, when you drop the current all the way down to 0, it causes the CC to turn on. So increase the current a little bit, and the voltage, check for the maximum voltage, 29.4, and plus there is precision, so you can go up to 30 volts, maximum 30.6, and the minimum voltage 2.6, and with the precision you can get down to, wow, 0 volt, even 0.1 volt, 0.2, and very stable. Okay, that's all for today, and it's a very long demonstration, and I hope you enjoy and you learn. Thanks for watching. I hope you enjoy our tutorial today, and please subscribe if you like it, and I hope you learn from me, and we will make some more videos in the future. You can please subscribe to my YouTube channel, and thanks for watching. Bye for now.